today I am back with a new section of craSHduMP, and it is a different kind of training series that I'm going to introduce to you. So here we would experience a kind of a mixture blend of MSP430 microcontrollers as well as some of the ARM Cortex M4 and M3 and M33 flavor of the microcontrollers. So today a very simple yet very powerful topic that I'm going to discuss with you, and it's going to help you in all of your product engineering designs as well as new POCs. So this is called in application programming. Some of them call it as in system programming. It is a part of the FOTA, that is known as the firmware over the air upgrade, and it is also a part of normal OTA, that is over the air upgrade. It can be firmware, it can be configuration, which is called a COTA. So the main thing, the main concept over here that is that I'm going to take a very basic kind of a microcontroller, that is MSP430 series, which is a 16-bit MCU from Texas Instruments, and this MCU is going to show to you that how we can do the in-application program update for those products that you've already designed in a lower memory footprint microcontroller. That can be some ST micro or PIC or AVR or any kind of MCU which supports flash programming. So the main thing that's behind this is that it has to support the flash programming, so that you can access the area of the flash from a separate section of the flash itself. It can be from the RAM also. That depends on your RAM configuration. If your controller is having a good amount of RAM, you can go for writing from the RAM to the flash, or you can also do it from the flash itself. So now let us dive deep into it. So the first thing that we need to know is what is the FOTA or OTA or IAP is used for. So it's a small kind of code that is sometimes that uses the company's own bootloader, which is residing inside the microcontroller. So the work of this bootloader is to load the newer version of the firmware that you push from the Git or other cloud services, or it can be from over any sub 1 gigahertz software, wireless connectivity. The main intention is that you release patches, you release newer updates, you release new versions, you include new implementations, and all of them have to go into the flash memory area. So now coming to the actual core of it, this is basically done in some categorized steps. The first step would be to check in an online web portal or in a cloud service that if a new version of the firmware is available. If you're releasing a new firmware or patch, then once a new version is available, it should be able to download the firmware and check for the integrity, which can be done using any kind of CRC or any kind of computation. And then after the integrity is valid, then you can replace the old firmware with a newer firmware, and you can then proceed with the boot. Now there are two ways to do it. One is you use the normal bootloader, and the bootloader, you have to invoke the bootloader during you can invoke the bootloader in multiple ways. These are out of scope of this video, because it will require a detailed study of the controller and the architecture that you're using. So if you're using a Linux platform, it will have its own grub bootloader or some kind of lower version of U-boot. You can also have in an RTOS, it can have its own bootloader kind of an environment, but the main thing is that there has to be a bootloader. So one option is that you can invoke the bootloader using some kind of pin or button. Usually the bootloader can be invoked using some button that is there in your device. You can check the hardware schematic diagram. It will help you to identify that how to invoke the bootloader using push buttons. Some of the controllers, they allow you to invoke the bootloader using some detectable UART patterns, which can be sent over the UART when the controller is booting. Some USB based bootloader is also available in the market, wherein during the booting process, if you are sending some valid data over some specific data over the USB, then you can actually invoke the bootloader. Now coming down to the use case that I have shown over here is Very simple. We are not depending on the internal bootloader. We are going to write a very simple kind of a bootloading code on ourselves, and we are going to implement it in order to replace the old flash program. So if we have a look at the MSP430 memory map over here, you can see that the basic implementation of the memory or layout is like this. You have the special function registers from 0 to F, which is 16. So there are 16 SFRs. After that there are some 8-bit peripheral module SFRs or memory allocations, because it's a memory mapped IO device, and there are some 16-bit peripherals. So these are the areas where you cannot do anything. Above that, starting from 0200 hex is starting the RAM location. Now the limitation of the RAM depends on your microcontroller variant. For the one that we are using here, it is MSP430 G2553. So over here the memory area will be spreading from 0200 to approximately, I think it's from 203FF, and above that is a flash. So now we will be concentrating majorly on the flash area, because we want a kind of a program that can reside inside the flash, and we can invoke it using some method once we detect that a new version is available, and that program from that area of the flash should be able to rewrite the original code that was present in your MCU. That is the main target. And apart from that, you also have to do some changes in the interrupt vector table, because once your controller comes out of the initial PUC, that is power on condition reset, or you can also say it as a POR or a power on reset, then there are certain memory areas or vector locations from where the memory execution, I would say the address is fetched by the program counter. Now ideally, if you're using CCS, that is Code Composer Studio from TI, they have pre-initialization codes which will execute your code from C000 location, but definitely you can customize and change it. I am not going to do all those things over here, because that is again out of the scope of this video. It's a separate task altogether. But what I can say is that it's best not to touch the C000 configuration that's there. We rather take a separate location, which I have taken here as D000 location, which is again within the flash ROM area. So it is D000, and from the D000 location we are going to boot our code instead of from the C000 location. So whatever code you develop and you write and you keep it inside your flash will be residing from D000, and all your code will start executing from D000. And the bootloader part of the code, which actually rewrites the flash memory, that will be residing in an upper memory area. I will show you inside the code what that memory area is. That is somewhere, inside in the upper part of the flash. Okay, somewhere around say F7 E0 or something like that, which is in the upper part of the flash. Good. Now coming to the launch pad that we are using, I'm using the hardware from TI, that is Texas Instrument MSP430 G2 launch pad. It's a very simple hardware. It has its own TI's emulator and the debug connectors, but I'm not going to use the debug connectors for the IAP. We are going to only program the initial code using the debug, this emulation. So good. So that's how we are going to take it off, and once the application is updated or changed, you will be able to see it yourself. So you will need this hardware. Right now I can show you. This is the hardware that we are using. It's the same as in the photo. So this hardware is going to be connected using the USB, and this controller will be will be reprogrammed using the new code that we will be changing. Okay, now coming to the actual part of it. So there are two in my workspace. There are two programs, right? So one is the normal a simple Blinky kind of a code. So this is the Blinky code. It's nothing. You can see it's absolutely nothing. It has only one line of watchdog holding. I'm configuring the P1 direction as output, that is P1.0. These two are commented. and I'm just toggling the P1.0 LED at the rate of approximately 1 second. So this is the code that is presently running, and you can see that the LED is toggling every 1 second. So this is the code that is running over there. So what we will do, we will be changing this value, this blinking value, to say somewhere around 40. So this will basically blink the LED faster. So I just want to show you that this is the code I am going to develop and download it. So just imagine that this is your original application, right? So we download the code. Oops. Just a moment, I need to replug this. These connectivity glitches are sometimes there in the boards, so don't worry about them. If you get them, just unplug and replug the board. Okay, so now you can see that this code is loaded, and first let me show you. You can see that the rate of blinking is quite fast now. Okay, as compared to previous one, it's quite fast now. Now let me show you that if we go back to the original program where we had done this, so here inside the debug you will see that there is something called the map file. Now what is a map file? The map file is basically a map of all the symbols that are generated and all the function placements that are generated based on your linker and your compiler. So here you can see that the actual flash area starts from C000, as I told you. That's the default flash area from TI. And you can definitely customize it, but I would suggest you not to. And here the code basically resides in this area of C000. Okay, so that is this one, the text area, the text region. Okay, now this is one part. The another part that you need to do is you have to right click on the project, go to properties, okay, and you have to enable the hex builder, that is MSP430 hex utility. Now what is this going to do? In order to do the FOTA, you have to send the program to your MCU either through Wi-Fi or through some other means. So here you will be needing the TI-TXT file which TI can generate in order to program your controller or your flash of your controller. So this hex utility you have to enable, as it is enabled from here, and then from the output options just go and select this format, TI-TXT HEX format. This is the easiest one. You can also select Intel hex, but I would suggest you go for TI hex. Okay, so it's already there in my case. So once you click on this text file, the .txt file, you will see that this is actually your entire opcode of your program that you've written. Now what does this have? This has the code that is there placed in the C000 memory location. So these are the operands and the opcodes for the actual code itself, right? And these are the values that needs to be placed in the vector locations, that are the interrupts. So you don't have to bother about the interrupts now, but later on in more complicated projects you will also have to program the interrupts, because if there is a timer interrupt, you have to write the timer program and you have to give the address location over there. That is the vector location of the ISR. So now what you're going to simply do is you're going to simply copy this, right? You're going to copy this and take it to another project. Both of these projects are available in my Git, and the links are there in this particular video section. If you're viewing it from YouTube, it's there in the YouTube comment section or maybe in the description section. If you're seeing it in LinkedIn, it will be there along with the video body. So you have to copy this and go to your next application. So the next application is actually the flash writing application, which I'm calling it as the IAP, that is an application programming. So what does this do? See, here you can see that I have copied the part of the code, which is starting from the address location C000. So let me clear out from here. So like, so this is actually those opcode values which were generated in your txt file. You can compare and see it. So what you need to do, you just need to copy from there to your actual code where you will be placing it. One second, I think I mistakenly deleted. Yep. Okay. So yeah. So now this is your code that is generated from your project which you want to update. Now after that, there is one more thing that you need to think, that as I told you, your execution code should start from D000, and your IAP code, which is going to program your flash with the new firmware, that has to be located in a separate location, obviously, because if you are within the region of D000, you cannot override the same region. So that is going to be written in the linker file. So the linker file on the left, you can find it in CCS. It is named as lnk underscore then the chip name .cmd. So over here you will come and see here that flash starts from C000, and I have divided the length to 37E0. The reason I will tell you. So why is it like from C000 to a length of 37E0? So the answer lies to the fact that if C000 is the starting address of your flash execution, code execution memory, then if you add 37E0 to it, that's going to give you F7E0. Now what is F7E0? In order to understand what is F7E0, we have to go to the interrupt vector table of this particular controller. So for that you have to go to the data sheet, and in the data sheet you can search for interrupt vector table, interrupt vector addresses, and here in the interrupt vector addresses you can see that these interrupt addresses are unimplemented, which means that they are not going to be used for any kind of vector interrupts. We will start from E4, that is for the port 1 interrupt, E6, that is for the port 2 interrupt, E8 is again unimplemented. So basically you can have your code till the area where the interrupt vector tables are not implemented. Okay, so just to be on the safe side, I've kept it as F7E0. So that F7E0, you will see that it's much way below than this vector table. So the F7E0 is my limit of the code memory, or you can call it as a text memory. And there is another part of the flash which is named as flash 2, which again starts from that location F7E0, where this flash ended, right? This flash ended at F730, and from F730 till, and from F730 my flash 2 starts, and that goes on to a length of 07F0. So you have to add 07F0 to this, and that will going to give you FFD0, right? Now again, going back to the vector table, if you see that FFD0 is, again you can see, is in this region, which is way below all the vector tables that are implemented. So your main intention, you have to keep in mind, is you shouldn't collide with any vector table, otherwise there can be a program crash. Okay, now these are the two flash areas that I have defined. Now why I have defined these two flash areas? Because C000 is TI's conventional memory area from where they start their own codes, and the next one, flash 2, is where my IAP code is going to reside. Now how do I tell that? That is explained over here. That dot my code section, so this sections area in the linker will basically tell the compiler that okay, this part of the code should reside in this part of the memory of the flash. So wherever I give the attribute as my code, that will be automatically placed in flash 2. And that is the reason why if you go and see that the IAP, when it is declared, that function where it is declared with the attribute dot my code, so that it is purposefully placed in that part of the memory area. And finally, here the function IAP that is implemented. Okay, so here you can see I'll explain in very basic form that what this program is written all about. So it's basically a simple code that starts with configuration of the clock, and then it opens the flash memory and it configures the flash timing generator, which means that the flash programmer module has some parameters that needs to be configured. So that is done over here. After that, we directly go into the IAP. So inside IAP, a simple flash pointer is declared, and that is initialized to the memory area, as I told you, is D000, from where we want our codes to be executed. This is, again, I'm telling you, IAP is not located over here. IAP is located in flash 2 memory area, okay, and this D000 is in the flash memory area. So both are different memory areas, right? So now after that, what it'll do, it'll erase the flash. Now one thing you must remember about flash memory is that the flash memory controllers, they need to be fully erased first. That is, that you have to erase it with all ones. So once this flash memory is divided into multiple pages or segments, and each page or each segment has to be first erased, where all its bits become 1, and then you can program your code so that you can have the zeros coming in, which means that you can turn a bit from 1 to 0, but you cannot turn a bit from 0 to 1 without mass erase. So this mass erase is required, or the erase of that sector is required first. So after that, this for loop, this key is also something that is very important, because without the key you will not be allowed to program the flash. So after the key is provided, then this particular for loop is doing nothing, but it's going to fetch the array values and it's going to write to the flash memory area, which is pointed to by D000. And finally, after the write is complete, it's going to log the flash. And once that is done, it goes back to here IAP. I have just given a no operation over here, in order to check with the debugger that what are the values that has been written. I mean, whether the IAP has been able to write the actual values. And once that is okay, I am just jumping to the D000 location using this function pointer. So this function pointer is simply like it just makes the controller or the program counter get loaded with D000 and it jumps over there. So one thing that you need to remember now is that when you are inside IAP, it is better not to open the debugger, because your IAP will be releasing the flash memory controller only after executing the last lines. Now if you halt it in between, the flash memory module, it actually generates a higher voltage in order to program the flash memory. So if you halt it in between, your flash memory will be stressed in order to check the values. So it's better to avoid that, because the flash has a limited number of read-write cycles for any of the devices. Okay, so once this is done, you can see this code is now, so this is your new code that I'm going to write, and this is with a slower blinking rate, whereas my default code is at a higher blinking rate. So I'm going to first check if there are any errors in this. So after that, I'm going to download this code. So now I'm flashing the controller with this IAP enabled code. It's going to take some time. Right. So now what happens, I can just give you a breakpoint analysis. So once it comes to the IAP, on the right side, I have kept the memory map of D000. So once the IAP is executed, that is, which means that right now you can see this D000 is fully erased and it doesn't have any code, right? So once the IAP is executed, it should be writing the entire memory, and that you can see in the red. So the updated firmware, which was there in the array, which should come from Wi-Fi, from your Git, or the server from where you want to update your device remotely, that code comes and sits in this location. So now when I jump to that particular memory location, it should be executing this particular code, and as you can see over here, the blinking rate has decreased, right? It has decreased. So if you hold the code over here, you can see that the program counter is now executing. You can see on the top the program counter is executing from the memory location D01A. So we can open the disassembly. Disassembly is nothing but the assembly code that is generated from your C code. So the disassembly, we can see it from view. Then if you go to disassembly, you can see that D01A is nothing but that decremental loop which we had coded over there. That is this one, this one, this one, the delay. So that delay is getting executed. So basically what is happening is you have updated your code using the text or the TI-TXT file or the hex code which was generated from your another project. So basically this project helps you to fetch the text file from some internet. Now that particular interface is not here in this project. I will try to integrate it, and I will give you another release of this particular code, wherein like you can actually connect to a Wi-Fi network using ESP, and you can actually download the code and do a CRC check on it, and then you can directly flash the code. But this is just a framework, a basic framework to understand that how you can generate, or you can write firmware which can support the in-application programming in MSP430, which can help you update your existing devices which doesn't support remote update or FOTA. So using this simple technique, you can download the code from your browser using HTTP or using different kind of web access mechanisms, and you can update your product. So thank you for watching. I'll keep you posted with upcoming updates wherein you can go for a full-fledged FOTA. Thank you for watching this video.